shallow neural networks for one given layer. And now we're ready to introduce deep neural networks. And the good news is that there's nothing more to understand really about the mechanics. The mechanics of deep neural networks are the same, the exact same ones as with shallow neural networks. We are just applying these feed-forward equations, the same feed-forward equations that we introduced yesterday. Instead of applying them only twice, once to find the hidden layer and once to compute a prediction out of this hidden layer. Now we will be applying it more than twice. So we will apply the feed-forward equation to the inputs to find the first hidden layer, and we apply the feed-forward equation of the same shape but with different weights, with different parameters. To the first layer to find the second layer, we apply it again to find the third layer, and so on and so forth, to a final layer that we decide this is a hyperparameter, how many layers we will want in there. We will denote it capital L. That will be the last layer, and the prediction will be a linear combination of a final hidden layer. So the mechanics are really simple once we understood the mechanics of the shallow neural network, because they are absolutely identical. The more interesting question is, why would we want to do that? Why would we want to add additional layers? Although we have seen, we have a result that to give ourselves enough units in this given layer, we can represent absolutely any function to arbitrary precision, to arbitrary accuracy with a shallow neural network. So why would we want to go deep? The bad news is I don't have a formal answer to give you, because a convincing formal answer doesn't exist right now. Many people are working on it, and that within a year or two we will have a formal result that will tell us in general and convincing terms what is it exactly we achieve by going deeper. And that will also, such a result will also give us some principal guidelines for deciding on the architecture of the network, how many layers we want, how many units in each layer, and so forth. At the moment, this is very empirical, trial and error, and largely a matter of, adapting known architectures that have been empirically demonstrated to work very well in similar contexts, and then adapt them through trial and error. Anyhow, there are, even though we don't really have a formal result yet, what we do have is a vast number of empirical results where it has been empirically shown in practice that deep neural networks work a lot better than shallow neural networks. And what we also have is kind of an intuition of why this is the case. What is it we're really doing with deep neural networks? Well, what we're doing is that in the first layer, the first layer consists in basis functions of the input layers. And the second layer are basis functions of the first layer. So these are basis functions of basis functions of the inputs. And the third layer are basis functions of basis functions of basis functions. So what is it we're doing in a deep neural network? We allow the model to compose basis functions. We allow the model to learn to compose basis functions at best from the data. This is what deep learning gives you, what shallow learning doesn't give you. So with an infinite number of units, you really need only one hidden layer, but this is an asymptotic result. In practice, with a limited number of units, if you have a shallow network, all you get are linear combinations of of a limited number of basis functions of the same shape but with different parameters. And you cannot only represent that many functions with that. With deep learning, in addition, you allow these functions to compose over one another and to train the network to find the best composition of these functions. So intuitively, that gives us that gives the network a much stronger representation power. It allows the network to attain a wider, richer space of functions with a limited number of units than a shallow network. To get an shallow neural network with only one layer, one hidden layer of 10 units. So then our prediction will be a combination of 10 basis functions of the same shape with different parameters. And now we allow ourselves an additional 10 units. Where, what's the best strategy? Where are we going to put them? One possibility is to add them to the hidden layer. Now we have 20 units in our hidden layer instead of 10. So what we are getting is another 10 functions that we can combine. These functions are of the same shape as the existing ones, right? Just with different parameters. So intuitively, we should feel that we're not increasing that much the the expressive power of a network. On the other hand, if we put these 10 units as a second hidden layer, then we allow basis functions to compose on one another, and we can reach a much richer space of functions. And the reason why it's really hard to demonstrate mathematically is that by not putting these units on the final layer, we lose something, and by putting them on the as an additional layer, we gain something. And it's not obvious to demonstrate that what we gain is in fact exponentially superior to what we lose by doing this operation, right? But the intuition is there. Composition is more powerful than just additional units in a linear combination. That's why intuitively deep neural networks should work best and empirically they do. We just don't have a formal result for that yet. So yeah, this is the power of depth. So mechanically now, this multi-layer perceptron, as we call it, is, as I said in the very beginning of this presentation, but now hopefully it makes a lot more sense to you. It's consists in a sequence, a repetition of these feed-forward equations, so it's always the same. You compute the layers sequentially, one by one, where each layer is a nonlinear scalar activation function applied to a linear combination of a previous layer. And that's how we propagate from layer to layer in order to get a final prediction from the initial inputs. So by a sequential application of these feed-forward equations with potentially different activations and certainly different linear weights for each layer. Okay, are you good with that? Good. So just a quick summary and notations, because the mathematics are very simple here, but we deal with a lot of data, and the notations are usually the hardest thing to get about neural networks. So this is for the case of a general deep ANN, not necessarily a multi-layer perceptron. So, and here I was also careful in my notations to show you clearly what are real numbers, what are vectors, and what are matrices, because that will matter a lot when we speak about computation complexity. So in a general deep network, the prediction starts with the inputs, which we call layer 0. So we say that the vector A0 is the vector X, our vector of inputs. To move from layer L-1 to layer L, we apply feed-forward equations. So we say that the layer L is a function, phi L, a vector-to-vector function in the general case, of a previous layer parameterized by a set of parameters, theta L. And this is what gives us layer L out of layer L minus 1. We have layer 0. We will eventually get to layer capital L, the last one. And this layer L is just our prediction, right? And this, we decided that it will be in dimension 1. So this is just a real number or a vector in dimension 1, which is the same. And last layer is our prediction. So the parameters here at every layer L, I have a set of parameters, theta L, which is a vector in some dimension dl. It doesn't have to be the same dimension for all the layers. And the complete set of parameters for the network is the union of the parameters of the feed-forward equations on every layer. So we have a vector theta 1, vector theta 2, vector theta 3, etc., up to the vector theta L. So ultimately, our prediction is a function of the inputs parameterized by all these parameters. And training consists in finding all these parameters theta to minimize the sum of errors on the training set for which we know the labels. So to minimize typically the sum of squared prediction errors on our training set. And again, it takes an iterative algorithms where all the differentials of the cost to every one of these parameters must be computed on every iteration. So if I call Ci the loss on example I, so that's my prediction, but my squared prediction error for the example I, then what I need to calculate on every iteration, that's all the dCi's over d theta L for all layers, J for all the parameters on this layer. So it's a large number of differentials. Now, the particular case of a multi-layer perceptron, this is the same, only now our function phi have a specific form, a specific shape. As we have seen, there are both mathematical guarantees and computational benefits to this particular family of parametric functions. So now our feed-forward equations consist in a linear combination of a previous layer followed by an element-wise activation, nonlinear activation. So it's the same thing. We start with a layer 0. These are our inputs. So A0 is X. And the feed-forward is now more specific. We get layer L out of layer L minus 1 by applying this feed-forward equation. And here you can see that the weights for every layer, we have a matrix of weights, right? Because we have the weights of all the linear weights of all the units in the previous layer, and we have different weights for all the units in the next layer. So this is really a matrix. We have a matrix of weights. We have where Wij will be the weight of the unit J of a previous layer in the unit of a unit I in the next layer, right? So at each layer, we have a matrix of weights and a vector of biases. And we get from layer L minus 1 to layer L by making a linear combinations of the AL minus 1 and activate them. And as before, our prediction is the final layer. That's just a real number because we decided that the dimension of the final layer is 1. So Y hat is A capital L. So now the parameters, we have a matrix of weights and a vector of biases for every layer L, right? So if we have 10 layers, our parameters consist in 10 matrices and 10 vectors. And training, of course, will consist in finding the best parameters W, so all these matrices and all these biases, so as to minimize the sum of errors on our training set, just as usual. Okay? So, which brings us to backpropagation. How are we going to compute all these derivatives, right? So we're finally coming into the core of the subject here. So the first times I gave this presentation, I found I did not introduce elements of multivariate calculus because I kind of assumed that the audience knew all that already. And actually, first few times I lost half of the audience because I just threw in some known results from multivariate calculus that were obvious to me, but I realized they were not necessarily obvious to everyone. So now I would like to start by giving you a few elements of multivariate calculus and how it works. Multivariate calculus is an extension of calculus to the multivariate case. It's not particularly difficult. It's usually just an extension in vector and matrix terms of the univariate calculus results that we all know from high school, and that they usually work exactly. They usually extend exactly as one would expect, but it's worth reminding them quickly here. So we will derive the differentials of cost functions in general ANNs, and then a particular case of MLPs, along with an algorithm to compute them extremely fast. Since ANNs and especially MLPs are sequences of matrix operations, we add matrices, we do matrix products, we activate matrices or vectors, more exactly element-wise, etc. In order to do that, in order to derive these differentials, we will have to apply matrix differential calculus. So I will introduce the few elementary results that we will actually use. And I also included a few links if you want to learn multivariate calculus more formally. I would recommend the Coursera lectures called Mathematics for Machine Learning. That's by Imperial College. I did not follow these lectures myself. I knew matrix calculus already, but I've had excellent feedback for these ones. Mike Giles from Oxford published what he calls an extended collection of matrix multivariate results. That's an excellent reference. You have all the important matrix calculus results in a few pages. Also, I came around this paper by R.G. Barnes. He's a professor in some Canadian university, if I'm not mistaken, but I found the paper quite helpful. And my colleague Brian Hughes, he published on ResearchGate a more advanced paper called AAD of matrix calculations, where he derives the derivatives of more advanced matrix operations like Cholesky decompositions and what have you. We will not be using this. We will not be needing this here. So first, gradient. So if we consider a scalar function of a vector, so f takes its inputs in Rn, r to the power n, and outputs a real number, then we call the gradient of x and denote it with this funny reverse triangle. That's the column vector of its derivatives. So the gradient of f applied in a point x will just be the vector of the derivatives df over dxi. A key property of a gradient that it is well known is the gradient vector gives the direction where the slope of f is steepest. This is a very well-known result, but I don't know if it's the case to you. To me, it's not an intuitive one. It's not intuitive at all, but the steepest slope of f is in the direction of its gradient. You take a vector, you calculate all the derivatives of x of f in a given point, all the df over dxi's, you get a vector, and it so happens that this vector gives you the steepest direction of steepest ascent from f from this point. This is a well-known result, but to me, definitely not an intuitive one. However, mathematically, it's demonstrated in one line, because to the first order, we know that f of x plus delta x, so if we take a step delta x from x, right, a small one, that will be f of x plus the sum of the derivatives df over dxi times delta xi. So that's the inner product of the gradient with a step delta x. And actually, as it's funny, my 16-year-old son just learned that in high school, that the inner product is the product of the norms times the cosine in between the two vectors. And so if for a fixed time step delta x, if we fix the size of a step that we will be taking over the function, then we can see immediately from this formula that the size of a gradient is whatever it is given. If we fix the size of the step that we're taking, then the modification of f is given by the cosine between delta x and the gradient. And so the steepest ascent will be in the direction where the cosine is 1. So it will be in the direction of a gradient. The steepest descent will be in the opposite direction. Then the cosine is -1. And if we take a step in an orthogonal direction to the gradient, we're not modifying the value of f to the first order, right? So this is represented here like here I have this is in 2 dimensions, x and y, and I have the levels of f represented by these funny lines. This is my point x where I start with. This is my gradient as I calculated it in f. And if I'm going in the direction of the gradient, this is where I get the steepest ascent direction, in the reverse direction, the steepest descent. And if I move orthogonally to my gradient, I don't modify f, so I move in a direction that's tangent to these blue lines. Okay? This is important to get because this is the basis for pretty much every optimization algorithm there is. Now, just to generalize, to matrix gradients, the gradient of f of x has the same shape as x, right? Because we say that f is a scalar function, so the gradient, the derivative of x to an object has the same shape as this object. So we'd like to generalize that to matrices. So now, if I have a function that goes, a function of a matrix that returns a real number, so it goes from r n times p into r. So then we denote df over dm, the matrix of its derivatives, that will be of the same shape, n times p, as the matrix. And in this case, the gradient will, well, it's not really a gradient anymore, but it's a generalization of a gradient. It's no longer a vector, it's a matrix, and it's the matrix of all the df over dmij. Next is a more important generalization of a gradient, which is the Jacobian. Now we consider a vector function of a vector, so a function that goes from Rn to Rp. Another way to look at it is to say that we have, this is a collection of P scalar functions, right? So in this case, if we look at the, if we conceptualize the notion of derivatives, what is the derivative of f? Well, we have to look at the derivatives of every one of these P results with respect to every one of its n inputs. So we obtain a matrix, no longer a vector, and it's no longer called the gradient, it's called the Jacobian. And conventionally, doesn't have to be the case, but most people write Jacobians with functions in rows and derivatives in columns. In other words, so you have row 1 is for the first output, the first function, row 2 is for the second output, row P is for the last output. And in columns, we have, and in rows, yeah, we have the derivatives with respect to dx1, dx2, up to dxn, okay? So this is inconsistent with gradients. If I have a Jacobian of a function in dimension 1, its Jacobian will be a row vector, whereas the gradient will be a column vector. So the Jacobian in this case will not be the gradient, but the gradient transposed. And this is a bit confusing with when we're doing the calculations. I don't like to have a notation for Jacobians which is inconsistent with gradients. So I'm going to do it the other way, but for the moment, you can just convince yourselves that how the chain rule works in this case, right? So if we now compose two functions, I have a function g from Rn to Rp, followed by a function f from Rp to Rq, and I'm looking at the composition of the two, so h of x will be f of j of x, okay? And that's a function that goes from Rn to Rq. Right? Now, when we talk about adjoint differentiation, we mainly talk about the chain rule for derivatives. So this is something really essential. And this is a direct extension of the scalar chain rule that we all learned in high school, whereby dh over dx, so the Jacobian of h, will be df over dg times dg over dx. So it will be the product of the Jacobian matrices of f with respect to j and j with respect to x. And because you know matrix product is not commutative, the order is important. And in this case, the chain rule is written out of function first. So it's really df over dj times dj over dx, right? But in order to avoid confusion between Jacobians and gradients, I'm going to use them the other way around. So we will write Jacobians consistently with gradients, with derivatives in rows and functions in columns. So the first row will be for the first output, the second row will be, the first column will be for the first output, the second column will be for the second output, etc., etc. And in rows, I will have the d over dx1, d over dx2, up to d over dxn. So this is consistent with gradient now, because the gradient is the same as the Jacobian of one-dimensional functions. That's a column vector for us now. And Jacobian is just a horizontal concatenation of gradients, because this guy is the gradient of x of f1, this guy is the gradient of f2, etc. So a Jacobian is now just a concatenation of the gradients of the different results of the p functions. Now, in this case, df over dx, the Jacobian is not of shape p times n, it's of shape n times p, and the chain rule is written in the reverse order now, inner function first, right? Because we define Jacobians this way, now we have that if h is f of j, if h of x is f of j of x, then dh over dx is still the Jacobian of h to x is still the product of the Jacobians of f to g and g to x, but in the reverse order. Now the inner function comes first. So it's dj over dx times df over dj. Okay. A particular case that we'll be using is this of linear Jacobians. So if this function from Rn to Rp is a linear one, that means that it exists a matrix of shape p times n, a, such that f of x is equal to ax, then you can convince yourself that the Jacobian matrix, the way we wrote it with derivatives in rows, is A transpose, right? Because each fi then will be the dot product of the ith row of A times x. So dfi over dx will be the ith row of A. And so df over dx will be a vertical concatenation of these ones. And because of the way we wrote the Jacobians the other way around, it will not be A, it will be A transpose. Okay? Now, something that we use a lot as well is is a particular case of a vector-to-vector function where we apply a scalar function element-wise, right? This is what we do with our activation functions. So then we have an scalar function f that we apply element-wise to a vector x to find another vector, right? So what is its Jacobian? Well, obviously, fi only depends on xi, and it's actually equal to f of xi. So the gradient of this fi is f prime in position I and 0 everywhere else. So the Jacobian is a diagonal matrix which diagonal elements are simply equal to the scalar derivative of f taken in xi, right? So which we denote as diag f prime of x. Finally, we also have sometimes vector functions of matrices. So we have a function that takes a matrix and returns a vector, takes a matrix in dimension n times p, returns a vector in dimension q. Now its principle, in principle, its derivative will be a 3D tensor. It's no longer a matrix because you have to take the derivatives of every element of a vector with respect to every element of a matrix. So that will be a 3D tensor of shape n times p times q that contains all these derivatives. An interesting case, and the only reason I write it here is because we will have to use it, is the case where it's a linear function, which means that it exists a constant vector v of size p, which is in this case the same as q, such that f of a matrix is just this matrix times this constant vector, right? And then we have that fi, the ith element of a result, is, well, only depends on the ith row of m, which is a dot product with this vector v, which means that dfi over dmi, so dfi over the ith row of m, that will be this vector v transposed, and dfj different of I over dmi would just be 0. Okay, and last but not least, our first, I would like to give you a first view of the important notion of adjoints. So consider a series of calculations where we have an initial input x0, or in some dimension n0, and we apply a sequence of vector-to-vector functions to this input x to finally obtain an output, I called it C in this case. So we apply x1 is f1 of x0. I'm dropping the parameters in this slide. So f1 is a vector function from Rn0 to Rn1. So for avoidance of doubt, this is a vector function, not necessarily a scalar function applied element-wise. And we get another vector, a result vector in some dimension n1. And we continue, we apply the function x2 to this result x1 that gives us another vector in dimension R2. We apply a third function, f3, all vector-to-vector functions. We obtain a vector x3 in some dimension n3, and so on and so forth, capital L times. So we finally have a vector xl in dimension nl. And to this vector, we apply a scalar function. And it's important, the last function is scalar because we are looking at sequences of operations that which final result is a real number. Remember, I told that many, many times. That's the only way AD will work in constant time. So we always, we really restrict ourselves to calculations which final result is a scalar number that we call C. Okay, so now consider the vector dc over dxl for some layer L, from some intermediate result xl. So I want the derivative of a final result with respect to this vector. So that will be a vector in dimension nl, because this guy c is a real number, okay? So first of all, what does it mean exactly? What's the intuition behind it? That means that we keep all the calculations up to xl constant. Then we bump by a small amount, one by one component of xl. That will impact the rest of the calculation, and it will impact the result C. So what we call dc over dxl is the vector of the sensitivities of a final result C from bumping by small amounts the components of Excel as they are calculated in this sequence of calculations. So all calculations before step L are fixed, and all computations after step L are impacted by the bump to Excel. And we are interested in DC over DXL, the sensitivity of a final result to small bumps in these intermediate results. Now, this guy is very interesting, DC over DXL, the derivative, the sensitivity of a final result to a small move, to a small move in some intermediate result Excel. And it's got a name, we call it the adjoint of Excel, and we call it, and we denote it Excel bar. So the adjoint of something, denoted something bar, is the differential, is the derivative, the sensitivity of the final result of some given calculation to this something, right? Your adjoint is the sensitivity of the final result to you. That's how it works, right? Okay. So what can we tell about the adjoint? One thing we can tell is the adjoint of Excel, of a final hidden layer here, of a last intermediate result, that will just be the gradient of the last function that I applied. So this is a function h here. It's not very, you can't read it very clearly, but this function I called it h. So the gradient of the last output, since C is h of Excel, right? It means that the gradient of Excel, the adjoint of Excel is the gradient of h, right? But what about all the other gradients here? And this is what's nice is, well, the whole point about this adjoint is that by a straight application of a chain rule, we get this adjoint equation. So what does it mean? What is the adjoint of Excel? Well, the adjoint of Excel, by definition, is DC over DXL. But how does Excel impact C? Well, it impacts C because it's used to calculate Excel plus 1, right? But because we only look at sequences of calculations that have this sort of Markov property, if you want, where each layer only depends on the previous one, it means that the only impact of Excel is through the calculations of Excel plus 1, which also means by the chain rule that this DC over DXL will be equal to, will be equal to DXL plus 1 over DXL, so the sensitivity, the Jacobian of the sensitivities of Excel plus 1 to Excel, times DC over DXL plus 1. But this guy, by definition, is the adjoint of Excel plus 1. And so we have this relationship between adjoint that is completely fundamental and that we call the adjoint equation, that the adjoint of Excel will be the Jacobian of FL plus 1, the function that's used to calculate Excel plus 1 out of Excel, times the adjoint of Excel plus 1. So you can see how everything is going to be reversed when we calculate derivatives, because when we apply the feed-forward equation, when we're making a prediction and looking at a prediction error, what we know are the inputs. And from these inputs, we apply functions in order, F1, F2, F3, up to FL, then H, to calculate C. So we're really going left to right. But with the adjoint, it's the contrary. What we know is the last adjoint, XL, because that's just the gradient of H of the last function. So we know the adjoint of this guy, and this equation tells us what is the adjoint of XL once we know the adjoint of XL plus 1. So adjoints are calculated in the reverse order. Yes, you know the last one, and you have a recurrence from the next one to the previous one. And this is why all our derivatives calculation will be reversed. Okay, that was the first touch. We will come back to that many times, no worries. So more formally now, how to train your network. Recap. We have a neural network of a general form, right? We're not on MLPs yet, implementing the following sequence of computations. I'm repeating this quite a few times so that you don't, you're not lost. We, starting with the inputs, x, in some dimension n0, we call this vector a0. We sequentially compute al from al plus 1 by application of some vector-to-vector functions, phi l, parameterized by vector of parameters theta l, to finally make a prediction y hat, which is the final layer, a capital L. So this is exactly the same visualization I had on the previous slide, except that here I made the parameters theta L explicit. I'm sorry you can't see much on the screen, but you can see it on your slides. This here is phi L parameterized by theta L. Okay. We also have a training set of m independent samples, xm, for the inputs, each one a vector in dimension n0, along with the corresponding labels a, y, m. And we want to train the neural network so its predictions correspond to the best predictions for y knowing x. I would like my network, when I give it an input x, I would like it to give me the best estimation that can be found for y once we know x. Now, fortunately, that concept, that notion, has a very well-defined mathematical object. It's called the conditional expectation. The best prediction that I can make for y knowing x is the expectation of y knowing x. And I would like to train my neural network so that it will give me the best possible prediction, so the conditional expectation. Now, by definition, as you probably remember from probability 101, conditional expectation is the closest function of conditional expectation given x is the closest function of x, the closest function, the closest function of x to y in the sense of least squares. So expectation of y given x is among all the measurable functions, the one that minimizes the expectation of y minus f of x squared, right? That's the definition of the conditional expectation. And so what have we seen and what do we know from previous knowledge? We have seen that if we give ourselves enough height and enough depth, my neural network can represent any function f to arbitrary accuracy by adjusting its weights, theta, which means that this universal representation theorem tells us that the neural network, well, at least a neural network of infinite size, can represent any function, right? But how does it represent any function? It represents it through its weights. So to a given collection of weights correspond one function. To every function correspond one collection of weights. So by setting the weights in the neural network defines the function that is computed through the network. So to choose the function and to choose the weights is really the same thing, okay? And also, we know, again, from probability and statistics 101, that if we have enough training examples, and if all these examples are independently drawn from the same probability distribution, then the expectation of y minus f of x squared is well approximated by the average square error, right? And here we can see why is it we want to why we want to train the network in these ways, why we always want to minimize the sum of squared error in the weights, because that means finding the function that minimizes the L2 distance of f of x to y, in other terms, finding the conditional expectation or a good approximation of it. Therefore, all we need to do, to some extent, is to find the weights, theta star, that minimize the mean square prediction error on the training set. And that will give us, at least asymptotically, a good estimate of the conditional expectation, which is the best prediction that one can ever make for y given x. Okay? Now, good news and bad news. There is all of these kind of guarantees that it exists an optimal configuration in the network that at least asymptotically so that at least asymptotically the network will give us the best prediction for y that can be made. That's really good news. What is not guaranteed is that your algorithm will find this optimal configuration, right? And actually there is, well, first of all, I would think evidently there is no analytical solution for the optimal weights, unlike with something very simple like linear regression. But there's more bad news. The cost C, so the sum of squared error as a function of all the parameters, is a non-convex function of the parameters theta. And there exists no algorithm that's guaranteed to find the minimum of a non-convex function. Such an algorithm does not exist, and it most likely, never will, right? So this is what caused mathematicians, our people, to turn our back on deep learning in the 1990s. We said, it can't be done. This is a non-convex function. Let's move on to something else. And deep learning was revived recently, not by mathematicians, by engineers who thought, well, you know what? It's not guaranteed to find it. There's no guarantee that it will not find it either. Let's just try and let's see how far we go. And, well, I think we can all agree that we went quite far. Empirically, it just works in many, many, many cases. Anyway, so, and the starting point is simply gradient descent. I choose the initial weights randomly, then I'm taking repeated iterative steps, always by a small amount, delta x, that's called learning rate in machine learning lingo, and I'm going to do these steps, to make these steps along the direction of steepest descent, which we now know is the direction opposite to the gradient. And that's it. There's nothing more to it. In the machine learning community came out with many, many heuristic improvements made to this algorithm. I'm not going to cover them but you will find them in the Coursera videos or in the deep learning book, for instance. But I have to insist that these are all heuristic improvements. None of them is guaranteed to converge any more than the naive gradient descent, right? These are just intuitive heuristic improvements that have been empirically demonstrated to improve things in some cases. That's it, right? Because at the end of the day, the function that we're minimizing is still non-convex, and there is no algorithm that is guaranteed to find the minimum for us. We know that this minimum exists, and we know that this minimum asymptotically gives us the best prediction that can be made, but we can't find it. Okay. However, again, about these heuristic improvements, if you look into them, they are very intuitive. So the intuitions behind them are understood, and we can take comfort in that they work remarkably well in a large multitude of contexts. But again, there's no guarantee, there's no mathematical result that tells us that, for instance, the go-to algorithm in the machine learning community now is called ADAM, and it's few heuristic improvements made over the naive gradient descent, and there is absolutely no maths that can show you that ADAM works better than the naive gradient descent. But it does in most cases, empirically. And intuitively, we can understand why. So now we still need those differentials. I've been stalling a little bit. So these optimization algorithms, all these learning algorithms start with a random guess and make steps according to the current gradient. So we must compute and provide the gradient dc over d theta of a cost to weights repeatedly. And our goal is to compute it quickly. So the reflex, if we don't know anything about it, and we just faced with this problem of maybe implementing neural networks for the first time in our lives, the reflex could be to go for finite differences. So compute a cost C0 with the current weights, making predictions for all my training examples, and to compute the sensitivity of the cost to each scalar parameter theta I. So each component of theta. I bump this parameter by a small amount epsilon. We compute the cos, call it C1, and approximate my derivative by C1 minus C0 over epsilon. FD is obviously linear in the potentially immense number of weights, therefore it is not variable. Okay. But it has very desirable property. There's something very desirable about this finite difference things, is that the implementation is straightforward and there's very little scope for error, right? I mean, this algorithm can be implemented in 5 minutes, and it's really, really hard to screw it up. Importantly, FD differentiation is completely automatic. Developers only write prediction, the feed-forward code, and FD will simply compute differentials automatically by calling this feed-forward code repeatedly. Developers don't need to write any differentiation code at all. Okay? More importantly, FD will automatically synchronize with any modification you make to the feed-forward code. So if you're going a bit deeper into deep learning, you will learn about some tricks of a trade to train deep nets faster, better. You have regularization, you have something like dropout, you have batch norm, and many more tricks of a trade. But all of these obviously modify the feed-forward equation, so it modifies the code, and so it affects the differentials. So every time you want to include everything new in your code, if you write differentials by hand, you will have to modify your differentiation code accordingly, right? But with automatic differentiation with finite differences, it won't be the case, because finite differences will just run your code repeatedly to compute derivatives, and whatever you put in your code will be automatically taken into account. So that's really great, only it's super slow. So what we are going to do now is that first we are going to find a faster way to compute derivatives, and then we will see how we can make it automatic. As it will never be as automatic as finite differences, but we will try to make it as automatic as possible. So this is our goal for the next 3 hours. All right? So manual derivatives with AD, adjoint differentiation. Well, since finite differences will not work for you, let's see if we can calculate these derivatives, the derivatives we need analytically. So recall the sequence of calculations in the network. It's got this neat, what I call Markov property with a slight abuse in wording. The important bit here is that every intermediate result, every layer, only depends on the previous intermediate result on the previous layer. And so the final result is calculated out of the initial inputs from a sequence of vector-to-vector functions. Now, we know the shape of these vector-to-vector functions, phi L. We know them, right? This is what defines the architecture of a network. This is hyperparameters that we have decided once and for all. We know the shapes of this function phi that goes, lead us from the previous layer to the next layer. We know the shape of this function, and when we calculate the derivatives, we also know the current weights. Remember, we started with a random guess for the weights, and we're iteratively moving them in the right direction. So when we're calculating these derivatives, we know the current weights. Okay. So this phi function, we know its shape, and it's a function of the previous layer, AL minus 1, phi L. So to find AL is phi L of AL minus 1 and theta L, the parameters. We know the shape of phi. We have decided it once and for all. We know the current values of the parameters. And we know AL minus 1 because here we will assume something that's important for AD, is that before differentiating anything, that we made all these predictions, we performed the feed-forward calculation, and that we stored all the intermediate results. Provided that we did that, provided that we stored the all the hidden activations, we know them when we are computing the differentials. And therefore, because we know phi, we know A, and we know theta, we know the derivative, the Jacobian of phi to theta and phi to a. That's my point here. So we want to quickly compute all the dc over d theta L, and each one of these are vectors. Now this cost, C, that's the mean or the sum of what we call losses in the training set. So that's a sum of squared. Yeah, each the prediction error on example I, we called it CI, and CI is just the squared prediction error for example I with the current weights, right? And the cost is the average of the sum of the losses. So we want to calculate the dc over d theta. dc over d theta evidently will be the average of the dci over d theta. So we can just focus on the derivatives of one loss c, where I drop the index I to simplify notations, and then sum them up in the end. Okay? So now what we're trying to calculate is dc over d theta I. Okay. And sorry about that. Okay, okay. And then this dc over d theta I, by the chain rule, in this calculation, you see, sorry, it's not theta I, it's theta L. It's the vector theta L of the parameters for calculating layer L out of the layer L minus 1. Okay, I know there's a lot of indices and a lot of notations. It's not complicated, but the complexity is, the devil is in the details. So I calculate AL out of AL minus 1 by applying this function phi L, right, with the parameters theta L. And this is the only place in the calculations that these parameters theta L are ever used. Therefore, by the chain rule, dc over d theta L will be dAL over d theta L times dc over dA, right? Because theta L is only used to produce AL. And this dAL over d theta L, since AL is theta L with the parameters theta L applied to AL minus 1, that will be the Jacobian of the partial Jacobian, if you want, of phi L to theta L times dc over dAL, where this guy here is known. We know it. We know the shape of a function phi, we know the current weight, and we stored the current activations. So we know this guy. Okay. So what does this tell us? That tells us that if I can compute all the dc over dAL, if I can simply compute the differentials of my loss to every one of these layers, every one of these activations, then I can find the desired derivatives of C to the weights by application of this formula, for which one of the terms is known. So then we can first compute all the dc over dAL, and then apply this equation to find all the dc over d theta. Okay, I do appreciate that this, if you're seeing it from the first time, it should not come, it should be non-trivial. We have a lot of data, a lot of different objects, a lot of indices and notations. And in addition, I did repeat yesterday that this is a little bit mind-twisting, even though these are very simple maths. The most complicated maths I used here are the chain rule. And so anyhow, so now our objective is to calculate all the dc over dAL. And again, we start with A0, that's our x. We apply a vector-to-vector function phi. We calculate A1, then A2, in a sequence A3, up to A capital L. And finally, my A capital L is my prediction, so my loss is y hat AL minus the label squared. Okay, and I want to compute all the dc over dAL. So, how are we going to do that? Well, it's not. It's still by the chain rule, we see that because my calculation has this neat Markov property that AL is used to calculate AL plus 1, which is then used to calculate AL plus 2, etc. So I can apply the channel and say that dC over dAL is dAL plus 1 over dAL times dC over dAL plus 1. Okay. And this guy, AL plus 1, is obtained from AL by application of a function phi L plus 1, parametrized by theta L plus 1. So this guy here is actually the Jacobian of phi L plus 1, the partial Jacobian, if you want, to AL. And this guy here is dC over dL plus 1. I just copied it, okay? And again, this guy is known. We know the shape of phi, we know all the activations, and we know the current parameters. So this one is something that we know that is given to us. This, you may remember that we already seen something like that 20 minutes ago. This is the adjoint equation for the adjoint of the activations AL over hidden layers AL. So AL bar, by definition, the adjoint of AL is dC over dAL. And what this guy tells us is that the adjoint of AL is a known matrix, a non-Jacobian, times the adjoint of AL plus 1. So I know it looks like there's a lot of equations here, but it's not as bad as it looks, because all I mean to say is that we can calculate all the adjoints dC over dAL in this way. So for instance, let's say, look only at the first line. This is the equation for dC over dA1. So the adjoint, the differential of C with respect to the first hidden layer A1 here. What is it? Well, by the channel, and still because my calculation in a neural network is neatly organized in a sequence, dC over dA1, that's dA2 over dA1 times dA3 over dA2 times dA4 over dA3, etc., etc., up to dAL over dAL minus 1, up to dC over dAL. Okay? It's just immediate application of a channel through this sequence of calculations. That's all it is. But then we know all the dAL plus 1 over dAL. That's since every AL plus 1 is found by applying the function phi L plus 1 to AL. All these guys, all this dA2 over dA1, that's the Jacobian of phi 2. And this guy is the Jacobian of phi 3, and this guy is the Jacobian of phi 4. This guy is the Jacobian of phi L. And this guy, very interesting, dC over dAL. But I just keep it as it is for the moment. But you can see that C is just the squared error, so dC over dAL, since AL and y hat have the same thing, that will just be 2 times y hat minus y, so that will be just 2 prediction errors. So this guy is known, and it's a real number. So what we are getting from these equations is that the derivatives that we need, the dC over dAL, they are matrix products. They're products of matrices that we know. And all we have to do is to compute this matrix product. So we really have our formula by a direct application of a channel. We know a dC over dAL, that's the product for the layers from L to capital L minus 1 of this Jacobian here, right? Times the last one, dC over dAL. And AL is y hat, it's the same thing. So I just copy this guy over, and I replace dC over dAl by dC over y hat, because it's the same thing. And C is the prediction error, the squared prediction error. So dC over dAl, that's dC over dy hat, that's 2 y hat minus y. So it's 2 prediction errors, and this is a real number. So this guy is just a real number. We just have to compute this matrix product. That's all we need to do, right? And I recall once again that all the guys, all the matrices that I need to multiply, all these matrices are known. The architecture of a network gives me the functions phi, hence I can calculate the Jacobians. The parameters theta are known for the current iteration on the current step. And these activations, all the hidden layer activations have been computed by and stored on a prior prediction step. So the only thing we need to figure is what is the most efficient way to compute this big matrix product, knowing all the matrices in the product. Okay? So for instance, let's focus first on the first layer. So DC over dA1. So we have seen this formula already. That's a straightforward application of a general. dA2 over dA1 times dA3 over dA2, tac, 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 up to dAl over dAl minus 1 times DC over dAl. This is straightforward general. We could compute it. So to compute this matrix product, have at least two strategies. We could compute it left to right, start with this one, right multiplied by this one, right multiplied by this one, and so on and so forth. Or we could compute it right to left. Start with this guy, left multiplied by this one, left multiplied by this one, and so on and so forth. So which is better? The natural thing, because we live in Western country, perhaps, is to go left to right. Left to right, in this case, means from layer 1 to layer L, in the same order as the prediction. To calculate it right to left will mean to calculate it in the reverse order from the prediction. Start with the last layer and finish with the first one. Okay? Back to front or front to back. These are at least two of the possible ways to calculate this matrix product. Okay. Now note that AL, this guy here, that's y hat, and that's a real number. And C, which is the loss, which is the squared prediction error, is also a real number. So the rightmost term, this guy here, this is a real number, DC over DAL. Okay? What about the second rightmost term? Well, AL, that's y hat, that's my prediction. So this guy is a real number. Okay? AL minus 1, that's the final hidden layer. That is generally a vector. So this will be the differential of a real number to a vector. That's a gradient. That's a vector. So we have a real number here. We have a vector here. And all these guys, all the previous guys are matrices. These are the Jacobian matrices. These are the Jacobian matrices of a function phi, of functions phi, that produce AL, which is a vector, out of AL minus 1, which is another vector. So we have all these guys who are matrices, but the last one is a vector. The one before, the second rightmost one is a vector, and the rightmost one is a real number. And why is that? That's because of one fundamental property that makes everything work here, is that we said we restrict ourselves to scalar calculations, to calculations where the prediction is one real number, right? It's not, the prediction and the loss are real numbers. So, to look at it visually, my DC over dA1, that's a series of matrix products, finally multiplied by a vector, finally multiplied by a scalar. So if we go forward, if we go left to right, we start with a matrix. We repeatedly multiply matrices by matrices to obtain matrices, which is, as you know, of cubic complexity. And it's only at the last calculation that we collapse into a vector by right multiplication with a vector on the final hidden layer. If we do it backward, we start by multiplying this number by this vector. So we start with a vector, and we repeatedly multiply matrices by vectors to obtain vectors, which is of quadratic complexity. So to calculate the same matrix product, to do it right to left, gives us one order of magnitude. to calculate the same number a lot faster by calculating it right to left than to calculate it left to right. And this is the principle of backpropagation. This is how we manage to calculate a lot of derivatives very, very fast. So what is the backprop algorithm? That's an algorithm that computes derivatives in the reverse order, as we have just seen, one order of magnitude faster. And once we understand that, the algorithm is kind of easy. First step, we need to compute a prediction by feed-forward through the network in order to store all the hidden activations AL, right? Because we will need that to calculate the Jacobians. Then we calculate all the DC over DAL, which we now call adjoints of AL, and denote AL bar, of all the layers activations, but in the reverse order. We start with the last one, with the very last one, which is my prediction, A capital L bar. That's by definition DC over DAL, which is the same as DC over DY hat, which is 2 prediction errors. So I know the last one. And then I can recursively compute all the DC over DAL. Okay, there's a mistake here. It should be L plus 1. So if I know DC over DL plus 1, the chain rule gives me DC over DAL. The adjoint of AL, by definition DC over DAL, that's the A over the A plus 1 over DAL times DC over DAL plus 1. That's by the chain rule. And again, there's an error here. And this guy, DAL plus 1 over DAL, that's the Jacobian of the vector-to-vector function applied to AL to find AL plus 1. So that will be this Jacobian, and this guy is, by definition, the adjoint of AL plus 1. So we know the last one, and we have a recursive relationship, a matrix by vector product, to find AL once we know AL plus 1. So we are going to find all the derivatives we need by repeatedly applying matrix by vector products. So that way we get all the AL bar, all the DC over DAL, all the derivatives of the loss with respect to all the intermediate activations. And that's in a single backward sweep, because we compute them all from one another. We don't need to compute first A1 going through the network, then compute A2 going through the network. We do it all in one single sweep, because we know the derivative of the loss to the final layer, to the output layer, and we have a relationship that gives us DC over DAL when we know DC over DAL plus 1. Right? And this relationship, again, is multiplication by a matrix. All the DC over DAL are vectors, and we know by what matrix we need to multiply them in order to find the sensitivity to the previous layer. And so we can compute them all in one single sweep through the layers of a network. But these are not exactly the derivatives we want, right? These are the DC over dA, so the derivative, the sensitivity of a loss with respect to the activations of a network. You remember, this is not what we want. We want the derivatives with respect to the weights. But we had in equations, we had derived a simple equation to find them. So the derivative with respect to sensitivities, we need to multiply them by this matrix, by this partial Jacobian. Sorry, so is this known partial Jacobian times the sensitivity to the activations. So once we know the sensitivities to all the activations from backpropagation, we can compute the desired sensitivities to weights by multiplying DC over DAL by a known Jacobian matrix of d phi L over d theta L, and that gives us the DC over d theta L that we need. So backpropagation is the name this algorithm was given in the machine learning community. In finance and in other fields, we call it AD, agent differentiation, and this is the exact same thing. The core of backprop is the recursive reverse equation, which is this one. Again, if my calculation is organized in layers where AL is a matrix, is a vector-to-vector function of where AL plus 1 is a vector-to-vector function of a previous layer AL, then the equation I have is that the adjoint of AL will be the Jacobian of AL plus 1 over AL times the Jacobian times the adjoint of AL plus 1. And we have seen this equation before. We call it adjoint equation. Backprop is the adjoint equation applied to neural nets. And actually, if you review the steps in our demonstration, you will see that nowhere did we assume that we were inside a neural network. The only thing we need a calculation that's neatly arranged in layers, where every layer is a function only of a previous layer, and we also need the final result of it to be a scalar real number. As long as these two conditions are met, you can apply backpropagation to get the derivatives very, very quickly. That's what I say here. It is applicable to any calculation as long as the final result is scalar, because then adjoints are vectors, otherwise they would be matrices. And the computation is organized in layers where every layer is a non-function of a previous layer only. I will show you very easily in a few minutes that any computation can be organized in layers. And this is what defines the so-called computation graph. So backprop is actually applicable to any computation as long as the final result is a scalar. That will be the only condition, since I will show you that any calculation, well, any numerical calculation, it's not true of any mathematical calculation, but it's true of any numerical calculation. Once an equation is translated in code on a computer, defines a computation graph, and the computation graph can always be arranged in layers that only depend, where each layer only depends on the previous one. So this is not really a condition, because this is always the case. So the only condition is that the final result is scalar, and it always computes all adjoints, all derivatives in a single backward sweep through the calculation graph. So let me think here. Okay, must be a torture for you guys, no? We just went through the most intensive part of a presentation, and I have to go now through these equations in the particular case of the MLP. So I suggest we suffer another 10 minutes, right? And then after the break, we can go to more applied things. Okay, so now the MLP, the multi-layer perception, we have seen that this is a particular case where this function phi L that computes layer L for us out of a layer L minus 1, given parameters which are now a matrix of weights WL and a vector of biases BL, that will be a scalar activation function applied element-wise, call it GL, applied to a linear combination of a previous layer, so WAL minus 1 plus B. We have seen that. Now, in order to compute the derivatives, it's actually convenient to split this layer into two operations. So we say that this is actually not one layer, this is a sequence of two layers. First, I take this linear combination of the AL minus 1, I call it ZL, right? And then I produce AL by an element-wise application of G to the element of ZL. So I basically, instead of considering it one operation on one layer, I consider it as two sequential layers. So why do I do that? Because it's much easier in this case to derive the adjoint equations. Because then where is it? Yes. Then I have my sequence of calculations. I start with layer 1, then layer 2, then layer 0, 1, 2, 3, etc. But each layer I split in two, right? So I have for what I previously called layer L, now I have two operations, both are vector-to-vector operations. First of all, I have a linear one, and then I have a nonlinear activation. So when I'm going to apply backprop, I'm going to go backward and, in the reverse order. So for each layer L, I will first backpropagate the activation, and then backpropagate the result to AL minus 1. So how does it work? Just as before, I know the adjoint of the last of the output layer, so what I called AL bar. I know that this is just equal to 2 prediction errors. And if I have already backpropagated up to layer AL, and now I want to backpropagate further to layer AL minus 1, then I have to backpropagate through these two operations now, sorry. So the first one is when I went forward, I knew ZL, and I activated it element-wise with J, right? So DC, so that gives me the adjoint of ZL, which I recall is DC over DZL. So that will be DA over DZL times DC over DAL, which is AL, which I already know, right? Because I'm going back to front. So at this stage, I already know the adjoint of AL, and I want to compute the adjoint of ZL, right? And this is given by this equation. And this is just a direct application of a chain rule, as usual. So what is DI over DZL? Well, we have seen that an hour ago when we have seen some elementary matrix calculus results, where we say, because AL is obtained from ZL by an element-wise application of J. So that means that DAL over DZL, that's the diagonal matrix of G prime, the derivative of GL, applied to the element of ZL. And so at the end, this adjoint of ZL, that will be this diagonal matrix times AL, which is a vector that I know, and the diagonal matrix times a vector, that will give us ZL as, as the diagonal elements of the diagonal matrix, element-wise multiplied by the vector AL. That's something that you can convince yourselves of. Okay? So that gives us the adjoint of ZL. And now, what was our first forward propagation step, and that's therefore our second back propagation step, going in the reverse order, is to find the adjoint of the previous layer, AL minus 1, as a function of the adjoint of ZL that we know from this step. So we know that we find ZL as a linear combination of AL minus 1. And we know from the chain rule that the adjoint of AL minus 1 will be equal to DZL over DL minus 1. So D, this combination over DAL minus 1 times the adjoint of ZL. And this is the derivative of a linear combination with respect to what is it that you're combining, and that will be, as we have seen, this matrix of weights transposed. And finally, we have all the sensitivities to the weights from the sensitivities to activation. Against this backpropagation will give us all the sensitivities, all the adjoints of all the intermediate layers, all the ALs, which are the DC over DAL, but we really want the DC over DWL and the DC over DBL. And these sensitivities are obtained from the sensitivities to the DALs by applying elementary matrix calculus. For instance, DWL, the weights, the matrix of weights for layer L, the only place where they're used is to calculate the activations AL out of the activations AL minus 1. Therefore, DC over DWL for DWLY for each row W, right? That will be the DZI over DW times DC over DZI. And that will be, yeah, the dz over dwy, but z is w times a, so this will be just the a transposed times the sensitivities, the adjoint of a zi. Okay, so this will give us a weights to this will give us the sensitivities to the weights, and the sensitivities to the biases are trivial because my z's are, well, a linear combination plus b. So dc over db, that's the same as the c over dz, and that's the adjoint of zi. Okay? So I appreciate that it's if you haven't seen these equations before, it's virtually impossible, or maybe I have geniuses in this class, but it should be virtually impossible to understand them on a first presentation. You need to figure them out for yourselves on the paper, from the slides, quietly at home. But if you spend an hour, I guarantee to you, these are not as complicated. They are tedious, but they are not as complicated as they sound. This is an elementary application of a chain rule and multivariate calculus. So finally, we get the MLP backpropagation algorithm, and this is the one that's usually given in literature and in textbooks and research papers and so forth. This is the one that's implemented in most frameworks. That's a particular case of a backprop algorithm applied to multi-layer perceptions, and the algorithm is actually just an adjustment of a general backpropagation algorithm. We still start by computing a prediction by feed-forward through the network, storing all the hidden combinations ZL and activations AL. And remember, first we combine the previous layer, we make a linear combination of it, we call it ZL, and then we activate these linear combinations to obtain AL. And we need to store them all. Then we compute the adjoints of all the activations AL, which are by definition DC over DAL, and also of ZL, which are by definition DC over DZL, of all the layer combinations and activations, and we compute them in the reverse order, as we have just seen. We start with the adjoint of the output layer, which is just a real number equal to 2 prediction errors with the current weights. And then we recursively compute, knowing AL, the adjoint of AL, we recursively compute the adjoint of ZL, which is an element-wise multiplication of 2 vectors. And then we have the adjoint of the previous layer, AL minus 1, by multiplication of this guy by the transposed matrix of weights. And finally, when we get the adjoints of all the activations, we can compute the sensitivities to all the weights and biases. The sensitivities to the biases are the same as the sensitivities to the linear combinations. And the sensitivities to the weights are obtained from the sensitivities to the activations by multiplication, by right multiplication. Yes, by right multiplication of a transposed activation of a previous layer. So that's the backpropagation algorithm for MLP. So what is its complexity? So recall when we have seen the feed-forward networks, the leading complexity was one matrix by vector product by layer. That's what we have in our feed-forward equations, right? To move from layer L-1 to layer L, we have a matrix multiplication. We left multiply AL-1 by the matrix of weights for layer L, and this gives us our leading complexity. So it's of quadratic complexity in the number of units, linear complexity in the number of layers. And in order to run backpropagation, we need a prior feed-forward before we do a backprop. Right? Then we have the backprop equations themselves. They are executed exactly once on every layer, but in the reverse order, to compute derivatives to activations and weights. So if we look at every one of these equations, we find that this one is an element-wise multiplication of two vectors. So this is of linear complexity, so it's negligible. This is the big one, right? This one here is a matrix by vector multiplication. So this one is quadratic complexity. And this one is also of quadratic complexity. Finally, this is just an identity. So we see that in order to make a prediction, we have one matrix by vector product for every layer. We can see that now for backpropagation, we have two matrices by vector products for each layer. Actually, we have three because we must run feed-forward and store the intermediate results before we can run backpropagation. So that's one. And then we have these two. This one for backpropagation itself, and this one in order to get the sensitivities to the weights given the sensitivities to the activations. And therefore, now we have three matrix by vector product for each layer in order to compute all the derivatives. And so, as promised, the complexity of a complete backprop to compute all derivatives is just 3 times the complexity of a feed-forward prediction. Get thousands of derivatives, maybe millions of derivatives, for the cost of making 3 predictions. That's it. One is a necessary feed-forward prediction to compute and store all the Z's and all the A's. Then the backpropagation itself, interestingly, takes only one matrix by vector product. So the core of the algorithm for backpropagation itself is actually 1 times a prediction, not even 3 times, right? You have 1 because you need to run a feed-forward prediction and store all the intermediate results before. Then the backpropagation is 1 matrix by vector product, 1 quadratic operation per layer. And finally, to translate the derivatives to activations into the derivatives to weights, which is what you need, that adds another matrix by vector product on each layer. So we can compute a large number of derivatives completely in constant time. The actual backprop is as fast as 1 prediction. The other 2 are for the prior prediction and translation into derivatives to weights. And that's completely independent of the number of derivatives we want. And again, it works because first, the end result is scalar. So its derivatives to vectors are vectors and not matrices. And this reverse adjoint propagation, this backpropagation, collapses matrix by vector products into vectors. So we have quadratic complexity, just like feed-forward. And all these derivatives are computed analytically and in one single sweep. There is no need to repeatedly bump many parameters one by one. You can also see from here that it's likely to consume significant memory, right? Because all the combinations and all the activations must be stored for all the layers before we can run backprop. And that's in addition to storing all the weights and biases for the current iteration, of course. So it is extremely fast and extremely efficient, but it does consume a vast amount of memory. So what about, we're 5 minutes away from the break. What about automatic backprop? Well, this reverse adjoint propagation, this algorithm is what is called backpropagation, backprop in machine learning lingo, adjoint differentiation in general, computes all differentials of a cost to the many parameters in a deep net, times similar to one evaluation of a cost, okay, shifts this remarkable result by reversing the order of the calculations in the differentiation. Now, hopefully, we understand why. It is the only viable means to train deep nets in reasonable time, and again, it relies on the cost being scalar, hence its adjoints are vectors. And we will see shortly that it applies to any scalar calculation, not just neural nets. However, this manual AD code, you see, to code all these equations by hand, this is this can be complicated and certainly prone to error, and more importantly, it can be extremely, it can be an operational nightmare to maintain and synchronize as you modify the feed-forward code. So next, we are going to learn to automate AD, to make this whole thing automatic, to have a computer, to have a machine backpropagate for you without having to write the backpropagation code. So that will be automatic adjoint differentiation. Now, note for the moment that ID propagates adjoint in the reverse order through evaluation graphs. So in order to automate AD, we will need to find a way to automatically generate these evaluation graphs so that we can backprop derivatives through them. And that's a fundamental difference between AAD, for instance, and automatic finite differences. Because finite differences, they don't need to know the evaluation graph to differentiate with finite differences. All you need is an executable. You need something to execute. And you execute it repeatedly to find an estimate for all the derivatives. That's it. But in order to backpropagate through a calculation, you need to extract the evaluation graph of this calculation. You need to know what is the order of the calculations, what is calculated in what order, and what depends on what. So an executable is not enough. You need to somehow extract the evaluation graph, and once you have extracted an evaluation graph, then you can run backpropagation over this evaluation graph. So that's what we will learn to do. Hopefully we'll have enough time to automatically produce this evaluation graph so that we can backprop derivatives through them. And not only for deep nets, but for any kind of calculation, including large Monte Carlo simulations. So this is where I would normally illustrate the application of deep learning to financial derivatives, but I think I may have to skip this chapter because I just won't have time.